of the blood cell that's made, that has an iron core. And it's a gas exchange molecule that changes configuration based on the pH that it's at. But anyway, it has a little bit of iron in every blood cell in your body right now. There's a tiny bit of iron. And where did that iron come from? It dissolved out of a rock first. And then that was taken up by a plant. Here's a plant. And that plant has roots. Look at these roots. Do you see those roots hanging there? Down in the soil. And what are they doing? They're pulling in the dissolved minerals in the form of nutrients that originally dissolved out of a rock. And then once they've taken that up, they incorporate that up into the tissues in the leaves to do photosynthesis. Look at the sun shining on this leaf right now. It's extraordinarily beautiful, actually, all the way up here. And now we're at the point where this plant is making a flower and making seeds. And in order to do all of that, it takes a lot of specialized nutrients in a lot of specialized molecules to do that work that is a plant. And most of those nutrients came from rocks, which in the form of soil made them available to those plants to take up. And we've got to talk about what plants are, because this is the other important part. There's 1 billion organisms in a single pinch of soil, but where do they get their energy? That's where the plant comes in. What a plant is, plants, most people understand that plants take in carbon dioxide and let out oxygen. Most people know that. But most people think that they're breathing carbon dioxide. They're not. Plants are eating carbon dioxide. They eat the atmosphere. This plant is taking in carbon dioxide from the atmosphere. And then it's taking that carbon dioxide apart and then putting it together into tissues, plant tissues, leaf, stem, wood, root, flowers. All of that is mostly carbon. And the carbon comes from the atmosphere. So in order for a plant to take carbon dioxide apart and then put it together into these tissues, takes energy. And where does the energy come from? Where do you think the energy comes from? Right up there, 93 million miles away right now. There's a ball of fire out there giving UV radiation to this planet right now. And these things called plants have figured out a way to take that energy and use it. Photons coming from this plant, from the sun, are coming and they're exciting electrons inside of the chloroplasts of this plant and making those electrons jump up higher orbital. And when they drop down, they release that energy in a chemical called ATP, which itself is just a molecule that contains a little bit of energy from the sun. And that molecule can then be moved around elsewhere in the tissues of the plant, and where needed can release that energy, break the carbon dioxide apart, and then put it together into carbon-to-carbon bonds. And that's what this thing is. It's a bunch of carbon-to-carbon bonds. In fact, most of the plant is carbon from the atmosphere. And here's the amazing thing, is inside of the tissues of this plant right now is the energy of the sun at the time of photosynthesis has been captured inside of these tissues. The energy of the sun from 2 weeks ago, when this plant was growing, is contained inside. The actual energy from the sun is in there. And we know this is true. And you know how you know that's true? Because have you ever lit a fire from a piece of wood? And the energy that comes off, look, I actually happen to have a piece of paper right here. This is a piece of paper. What is paper? Paper is wood, right? This was once a tree. And here's a match. And if I get this match, this piece of wood of this match, if I get it hot enough, 451 degrees in fact, it will oxidize. Burning is a chemical reaction called oxidation. And in order for this thing to oxidize, I have to add enough energy to overcome the activation energy necessary for the oxidation reaction called burning to happen. And once something starts to burn, it produces its own heat and continues the chain reaction of the oxidation reaction, overcoming the activation energy necessary for the oxidation reaction to occur. And here's how we get this oxidation reaction to start, is we create enough friction and a flammable substance, right? These matches are from Brazil, and I've had them for like 10 years. So I was wondering if they were going to work. Whoa, they're kind of blowing up on me. Fortunately, I happen to have a lighter right here. And if I get this piece of paper to 451 degrees, what's going to happen to it? It's going to start on fire, right? And pretty soon, I can stop adding the energy from the lighter, and it's producing its own energy, and it's overcoming the activation energy, and this reaction is continuing. And you might notice that it's going away. Where is the paper going? Why is it going away? Oh, there's my fire alarm. Hang on a second. Hold on. Fire alarm. Don't tell my landlord. Okay. Okay. Look what's left over, though. After the fire is more or less out, you know what's left over? This stuff. This stuff right here. This is called ash. And you know what ash is? Ash are the minerals. Look what's left. I'll put this fire out. Hang on a second here. After the fire is out, we're left with minerals. Minerals don't burn. The carbon dioxide, the carbon went back to CO2, water vapor, and heat was released. And what is heat? Heat is the energy that was from the sun. And then what's left over is ash. Excuse me. I mean, that's what a plant is. It's energy. That's why it's food. That's why we eat it. I can eat this. This is a sprouting piece of, it's pretty good actually. And when I eat that, I'm delivering that to my stomach, and inside of my gut are the billions in a single pinch that are inside of me right now. And what they do is they ooze out enzymes. And enzymes are chemicals that lower the activation energy necessary for the oxidation reaction to happen. So there's literally a fire inside of you right now that's at a lower temperature because it's being mitigated. It's being made more efficient through the use of enzymes that are oozing out of these bugs. And what's left over in the fireplace? Minerals. And what's released? Nutrients, carbon dioxide, and energy. And that's why you eat. And what do you eat? You eat plants, or you eat animals that ate plants. And where did plants get their carbon? From the atmosphere. Where do they get their nutrients? From dissolved rocks. And where do they get their energy? From the sun. And that's it. And what comes off of a fire? CO2, water vapor, and heat. What's coming out of your mouth every time you exhale? CO2, water vapor, and heat. Look at CO2, water vapor, and heat. And how do you get a fire to burn hotter? You add oxygen, right? So that's why we breathe in oxygen, exhale CO2, and ashes are then, the ash is actually being distributed to every cell in our body via the bloodstream. And that's why you're alive. And that's really what's going on the planet. Yeah, all the energy is coming from the sun. What do you think gasoline is? It's old sunlight energy that was captured by carbon-to-carbon bonds in ancient plants. And when you get it hot enough, get it to 450 degrees, it burns and it causes, the heat causes the air pressure to expand, which pushes the piston down, which makes the crank go round, and that's how it works. And what comes out of the tailpipe of a car? CO2, water vapor, and heat. What comes out of your breath? CO2, water vapor, and heat. What happens to plants when they rot and they die and they're put back into the soil? The bugs, the same thing that's happening inside of your gut right now happens in the soil. And CO2 comes out, water vapor, and energy is released. And that's what the billions in a single pinch are doing. They're eating the dead stuff. And what is the dead stuff? CO2, water vapor, heat, and mineral nutrients. And really, that's how the whole planet really works. Everything else is sort of a sideshow, actually. I mean, really, it's like we live in a giant solar system. You know what I mean? In fact, we do. We live in a giant solar system on a giant rock where there happens to be liquid water, and that water dissolves the rocks, releases the nutrients, and these amazing things called plants have figured out a way to capture those nutrients, carbon and energy from the sun. Look, 93 million miles away, there's a ball of fire. A chemical reaction is going on out there, a nuclear reaction that is giving this UV radiation to the planet. And these things fix that into carbon-to-carbon bonds. And then when it's released upon oxidation, it's released as infrared heat. And that's why I'm getting a little sweaty, and that's why we're warm. That's the energy of the sun. So the next time you're sitting in front of a fireplace and you're warming your hands by the crackling fire, just close your eyes and feel the energy coming from that fire and know for a fact that it is energy from the sun that is captured in the carbon-carbon bonds of a living plant in soil. It lives in soil. And without the nutrients, the micronutrients and the macronutrients, those biological processes could not happen. That's what soil is. And everything else flows from that. Everything else is a sideshow to that. Everything else is up in here and is a fantasy. The only thing that is real is that we're in a rock that's dissolving in water, and we're going around an energy source. And you know what? There's a lot of other suns out there, and there's a lot of rocky planets out there, and some of them have probably got water on them. And I'll leave you to the rest to think the rest of that through. So it's all about soil. So let's look at some slides real quick here. Right here. There we go. That was half of the talk, but really, that was the important part of this talk, because now we can really talk about how soil works. We sort of know conceptually what it is, but now we're going to actually look at it. It's all about soil. I want you all to scream soil right now. Just do it. Just do it. Soil. Just do it. Right? All right. Look, here's a couple of soils for you just to think about. You may not realize this, but there are 20,000 different named soils. We name them, just like plants and animals have different names. So do soils, because there's lots of different rocks in different places, and there's different amounts of water, and there's different amounts of energy being captured. There's different life forms that are capturing that. On the left here, what do you see? You see something called an aridosol. What do you think that means? That means arid, right? So that means dry. So do rocks dissolve in air? No, they don't. So if you look at this soil, if you can see my pointer, the soil is actually very, very thin. In fact, most soil on the earth is very thin. In fact, we're losing soil, topsoil, at about 2 hectares every 8 seconds. That's a lot. And a lot of it's just being built over. Look where all the major cities are in the world. They're where there used to be. That's where the good soil was. Why do you think Paris is where it is? It's next to a river, because it would flood. And what was in the floodwaters? Nutrients. And sand and silt and clay and fresh nutrients. And that's why people farmed there. And they farmed there long enough that they actually extracted extracted the value from it and could trade it and become a city. And eventually they paved the whole thing over. And on the left here, we see what's called an aridisol. And an aridisol is a dry soil. So there's not a lot of water here. So there's not a lot of nutrients. And it's really hot and dry there. And so to live there, you have to look like this. I mean, it's a hard living there. But even in this soil, even in a single pinch of this soil, there's over 1 billion living organisms. They're just adapted to this life here. And I don't know if you can see this layer right here. You know what that is? That's salt. That's the salt layer, because it doesn't rain very much here. So the water dissolves a little bit of the salts. They move down with gravity, and then it stops raining. And then it dries up. And that just keeps happening over and over and over for 10,000 years or 1 million years. And pretty soon you've got a layer of salt, and these salts never get down to the groundwater, which could be 750 meters deep in a place like this. So these salts never get to the ocean. So this is salty soil. And in salty soils, you got to look like this to live there. Now look on the right. On the right-hand side here, we have what's called a mollisol. Now these are 2 of the 12 soil orders, of which all of the 20,000 different soils, they belong to one of these 12 soil orders. On the right here, you'll see a mollisol. And what this is in feet, you can see how thick this soil is. It's like 2, 3, 6, 10, 15, 20, 30 feet deep some of these soils are. And these are in the valleys. And here, it rains just enough that stuff can live and die there. The roots of plants are injecting themselves down into the soil, and then the plants die. And they leave behind a little carbon, energy, and nutrients. And they grow again, carbon, energy, and nutrients, carbon, energy, and nutrients. And that feeds the billions in a single pinch. And this dark soil layer here is filled with organic matter and lots of biological activity, which is turning over the carbon, energy, and nutrients and making them more available so more plants can grow. And the more plants that grow here, the more carbon and energy get into the soil, which feed the billions, which make it better soil so more plants can grow there. And the more plants that grow there, the better the soil gets. And the better the soil gets, the more the plants grow there. And pretty soon, you have what's called a mollusc. And that's what soil building is. It's the accumulation of carbon from the atmosphere, energy from the sun, and all these nutrients being exchanged through these billions of different organisms.
Aerosol and mollisol. Okay.
Yeah. And if you look down here, you can see at the base down here, this little white spots. Those are little bits of carbonates. Those are salts. And they're important salts that are there for plants too. Now you might be thinking, wow, let me see if I can get this to work. Here are a couple of soils. Look at these 2 soils, the iridosols and the inceptisols. 1/3 of the Earth's ice-free surface are these kinds of soils. And so they don't grow a lot of food for humans. 1/3 of the ice-free surface. And this one on the right here is called an inceptisol. And yeah, it's got a little bit of organic matter in it, but it's all these rocks. You got to take all these rocks out first. And once you've done that, there's not much soil left. So these kinds of soils are not building sophisticated technological societies. Because of the invention of agriculture, we are sitting here tonight using Zoom platform to communicate with each other. That's because the invention of agriculture. Look, before the invention of agriculture, people traveled with the seasons and traveled with the animals that were traveling with the seasons, and they lived off of them, and they had to carry everything with them. And probably they came back to the same site every year. They came back to those same sites every year. And when they came back, they realized, oh, here's these seeds, we can eat them. And let's pack them up and take them with us. And every year they cleared out some of the crap around the seeds and those plants. And every year they came back and there was more. And pretty soon there was so much surplus that they couldn't carry it with them. And they said, what are we going to do? They said, well, why don't we just stay here? And that's when that was the invention of agriculture, is when there was surpluses, too much to carry. And so they hung out, they dug a hole, they lived in a hole, and they got all the grapes and they put them into big clay vessels and they lived underground and they ate the grapes and the grapes fermented and it got darker and colder and they made it through the winter because the grapes fermented and it got them through the dark times. And then the sun came back and they praised the sun and they learned how to do agriculture. And everything has flowed from that since. The life that you live is because of agriculture. Now, most of you probably aren't growing your own food. That's because agriculture leads to specialization. And all of you, there's like 70 or 90 of you on this call right now. 90 different people, each one of you is a specialist at something. And that's because somebody else is growing the food. And because of that, there were libraries and books and written language and universities because of the invention of agriculture. And from that came people who invented this digital mouse and this computer that I'm talking about right now. They weren't growing the food. Brain surgeons, heart surgeons, specialists. And that's why we live the way we live, is because of the invention of agriculture. But it's all about plants that lived in soil where it all comes from and where it all goes. Sooner or later, all of it goes back to the soil. Sooner or later, doesn't matter what you want, what you wish, it's going to end soon. So celebrate this moment. Think about this moment in the history of the cosmos. We are here together right now in time together, thinking about what really is happening on the planet. And that's what we have to focus on. This is what matters. This is what matters. Everything else flows from it. The soil provides, and every economic decision you make should be in the context. Every economic decision you make should be in the context of, is this good for soil or isn't it? Because if it isn't, it's not going to help us. It's going to hurt us. So I want to go back to this slideshow briefly. So I want to show you the global soil regions. So here they are, the 12 soil orders, of which 20,000 different soil types belong to. And if you look in this scheme, you can see where the mollisols are. Look at this. United States, 21% of the land mass of the United States is in mollisols. Worldwide, it's 7%. That's all you need to know about why you're sitting here right now in relative safety and comfort and security, probably within arm's reach of food, looking at a computer, experiencing this moment, is because we have more mollisols than any other country in the world, except one. I don't know if you can see where it is. It's right over here, Russia. And what is it about Russia and the United States that you've noticed in history? They are in a constant power struggle for controlling the planet. And why is that? Because they have the good soil. Because they have the good soil, they have the good universities and the good technologies. And they can develop intercontinental ballistic missiles. Talk about specialization. Now look where the iridosols are in the world. Here's where the iridosols are. These are the troubled spots in the world. You can't make thermonuclear weapons from an iridosol. In fact, you can't even grow food security from an iridosol, especially in a world that's dominated by those who do have that kind of power. And look up here in this northern high latitudes. These are the frozen soils up here. These are called gelisols. And these little brown areas here, these are the peat soils that are all peat moss. And look in the tropics. You see this red area here? If you've ever been to the tropics, you know that the soils are red and yellow and pink. And those are oxisols. And what those are, you might think that they're really good soils, but they're actually not very good soils. Because mostly what these oxisols are rust. What's left over, the last thing to dissolve out of a rock is the iron, and the iron oxidizes and becomes rust. It's the most abundant element in the Earth's crust is iron. And so you might think, oh, aren't the tropics super like good soils? No, they're terrible soils because most of the nutrients are in the ocean, being sharks, because it washed all the nutrients away. These are ancient soils in hot, wet climates. And most of the nutrients, you might say, well, what about the jungles? Most of the nutrients are being cycled in the living biomass above the soil. The minute a leaf falls off a tree in the tropics, before it hits the ground, it's being ripped apart by an ant, turned into an ant. Before that ant can go to sleep, it's being eaten by some other insect, which is being eaten by some animal. And then that poop goes out of that animal and goes right onto the roots of a plant, just sucks it back up and never gets into the soil. In fact, these soils are very nutrient poor. They can't store a lot of nutrients. So really, what you're looking at here is not a map of soil regions. This is a map of political power. Because they who have the good soils have the good agriculture. And they who have the good agriculture have specialization. And they who have specialization truly have global reaching power, like real power. And where does that power, actual power, come from? The sun. Every beat of your heart is energy that was captured by photosynthesis of a plant that lived in soil. And either you ate it or your mom ate it. And that's why it's there, because of that. And that's a fact. That's a fact. I'm getting all worked up here, and I'm getting warm because I'm using a lot of food energy that I ate today. Here's what an oxisol looks like. It's mostly rust. It doesn't hold a lot of nutrients. It doesn't have a lot of nutrients. It's the leftovers. It's like the skeletons of rocks or rust, right? Here's the 12 soil orders, a map of soil orders of Oregon. Super interesting. We have these volcanic soils here in the Cascades. Here we have uplifted marine sediments along the coast. And then we have the Willamette Valley, which are these giant floods. The largest floods ever have known happen on the planet Earth happened here about 14,000 years ago and brought all these sediments in here from somewhere else. And up here, what's kind of light green, those are actually the Jory soils, or red soils. The scheme of the color here isn't very helpful. And then we got these desert soils out here, and Rhizosphere and Inceptisols. In fact, we have 10 of the 12 soil orders we have in Oregon. So a super interesting place to study soil. We don't have oxisols like the tropical soils, and we don't have the frozen soils like gelisols, which require very specific requirements like permafrost, etc. Here's the coastal soils. These are the spotosols. These are all sand dunes, ancient sand dunes. I mean, before the last ice age was over, the ocean was 60 to 600 miles further off the coast. And all that was giant sand dunes for 600 miles or so off the coast, the continental shelf. And those sand dunes slowly dissolved, and salts moved down through them, and things lived and died and lived and died. And pretty soon they started to turn into these soils. Soil is transformed geologic material. What you're looking at here is a big pile of sand. That stuff has lived and died and lived and died and lived and died and lived and died here so much that there's this black stuff called organic matter, which is carbon, energy, and nutrients. And the bugs, the billions in a single pinch, are living in here. And the types of vegetation that we have on the coast, when they decompose, they cause these very strong acids. And those acids move down through the soil here, and they dissolve out iron and aluminum, which precipitates down in this lower horizon here. So you can see that soil is a self-organizing natural body, a transformed geologic material, a living thing, a single pinch of which has over 1 billion living organisms in it. I'm going to skip ahead a little here. Here's soil. Real soil doesn't come in a bag. Soil forms over time. When rocks dissolve and energy is introduced into the system because of photosynthesis, and it's reorganized. If you look here, look carefully, you can see this little bit of iron oxide here. You can see some clay films here, and you can see these old root channels right here. You see that? Those cracks? That used to be a root. And what is a root? It's carbon from the atmosphere and energy from the sun, and it pushed the soil away. And then the root died. And then it went back to CO2, water vapor, and heat when it was biodegraded in a slow fire at low temperatures and exhaled out as CO2. And it left behind this crack in the ground. And the larger pores actually drain. So think about this. An earthworm makes a hole in the soil using the energy of the sun to do that. And then the earthworm dies. And what's left behind is an old worm channel. Now, when it rains, raindrops go down, they drain in the large pores. And think about a raindrop going down a worm channel, an empty worm channel, the worm long dead, and that drains down. And think what's being sucked in behind it as that water droplet moves down that pore. What's being pulled in? The atmosphere, oxygen. And what do the billions in a single pinch need? What do you need? Oxygen. You need to breathe oxygen to have something to dump electrons onto from the food you ate to create ATP in your cells, to do the work of building your tissues. And next time it's raining, just go outside and put your ear down to the soil and listen to it. It's gurgling. It's going like that. And when the soil is draining, when it's raining and the soil is draining, the soil is breathing. That's how the oxygen gets into the soil. And that's why pore size and managing soils for good drainage is so important. Plants need air at their roots all the time. Plants need water at their roots all the time. And the way that works is small pores hold water against the force of gravity like a sponge. Large pores drain into the force of gravity, allow for air entry. And that's what the billions in a single pinch need too. They need air and water all the time. Bottom line, soil is habitat. If you get nothing else out of this talk tonight, if you can understand that soil is habitat, the most diverse habitat on the planet Earth by any measure. And if you know that, if you can internalize that, you know what to do to it and you know what not to do to it. And every economic decision you make should be in the context of that, in my humble opinion. So I want to get to some other stuff. But what's really, I don't know where we're at on time here. Yeah, we're getting close to the end here. What I want to get to is with that in mind, let us go to where we were going to meet at our site for this talk. And I have to find that address. Hang on a second. Don't look at my emails. Here we go. And I have the address from our talk. Here it is. We are going to meet at 38970 Kings Valley Highway in Philomath. Now I can take you there by Google Earth and we'll look at it. But before I do that, there's a really cool plugin that's from the California Soil Resource Lab. Write that down. California Soil Resource Lab. You just Google that. And you look, when you get there, it looks like this. It's like the home page. And you go to Soil Web Apps and you click on Soil Web Earth and it loads this into your Google Earth. Now, all of the Natural Resource Conservation Service soils data, or much of it, is now been loaded into, this is going to work, into Google Earth. And there it is. See this? Soil Web. So now I can put in our address and we'll just fly there. Let's just fly there and have a look at it, okay? So we're zooming in. Now, this only works in the United States of America, where we have all this data digital. And what you're seeing now, this is where we were going to meet, and you'll see these lines will pop up. And what these are the boundaries of the different soil types. Remember I said there's over 20,000 different named soils? Well, here's a bunch of them right here. This is where we were going to drive in and meet. I think this is pretty close to where we were. I think we were somewhere between here and here. And I can click anywhere in these polygons, like here, this thing right here, and it'll tell me the soils that are there. And for instance, this is Abaquah. And Abaquah is a cumulic ultic haplozerol. Everybody say that together, ready? Cumulic ultic haplozerol. It ends in all. Which two soil orders did we talk about tonight that ended in all? Mollisol. So this is a mollisol. This is one of maybe 1,000 or more different types, or maybe a couple thousand different mollisols. And Abaquah, and you can see if we click on the actual name of it, it tells us it shows us an image of what it looks like at depth, 15 centimeters, 53 centimeters, down to almost a meter. And we can see how dark it is here. And that's because it has a lot of organic matter in it. In fact, having a certain amount of organic matter in the surface is one of the things that makes a mollisol, which is very different than an iridisol. And all this information, check this out. Here, look at this. Here's the organic matter at depth from 0 down to 152 centimeters. At the surface, it has near almost 5% organic matter, which is actually a lot. And look at the amount of clay it has. Clay is just a fine particle, and fine particles have fine pores which store water against the force of gravity like a sponge. Here's the sand. It only has about 15% sand. Here's the pH. Here's the salts. Look at all the salts are at 0. Why is that? Where are the salts here? They all went to the ocean, right? Because it rains enough here that the salts don't accumulate in the soil. They end up in the ocean eventually. And here's something we didn't really talk about because we don't have much time, is the cation exchange capacity. And what this number represents is the amount of nutrients that can be stored by the soil. Now, it's something we just really didn't have time to talk about, but soil, when it has clay and organic matter, clay is made when rocks dissolve and recrystallize. It's a secondary mineral. It's a mineral, a special kind of mineral that has a negative charge on it. And that negative charge can store positively charged nutrients. So soils that have high clays, especially in this part of the world, have the ability to store a lot of positively charged nutrients, nutrients that would have otherwise had gone to the ocean and become sharks. So soil, when it has clays, it can store nutrients and not have them wash away, which allows more plants to grow there. And the more plants that grow there, the more carbon and energy are added to the system, and the more biologically complex the soil becomes. And we end up having more organic matter accumulate in the surface. So clay and organic matter are kind of these secret sauce. The secret sauce of soil is clay and organic matter, because these two things are the energy and the carbon and the nutrient storage. And once you have those, you end up with a mollisol, or at least you can. So let's go back, see where we were. So we were just looking right here where these mollisols are. And you'll notice that's where they're doing agriculture. Look down here. There's some sort of farming operation going on here. What kind of soil is there? Abaquah, a mollisol. Look, Chehalem, another mollisol. These are all different kinds of mollisols, with the exception of this Waldo here. It's also a mollisol. So that's why they're doing agriculture here. Now we go down by the creek a little closer where it periodically floods. And what do we have? Well, we have some mollisols there too. In Oregon, in the Willamette Valley, we're pretty blessed here. I think there's some other places. This is a mollisol. Here, what's this? This is river wash right in here, because this is where there's a river. And what are river washes? Well, river washes are mostly sand and silt and rock. And let's just look. There's no data on this. It doesn't even have a name because it's not really an important soil. It's poorly drained. Let's see what else we have here. We were going to be walking along here. Here's a bridwell or bridewell. So what I want you to be able to do is I want you to be able to use this tool. And in fact, it's available to you on your phone. If I can find my phone. I don't know where my phone is. But you can find it. You just go to your app site, and you look for Soil Web app. And the Soil Web app is actually just same kind of data, just right on your phone wherever you are. So I don't think we should really dive into much more. I'd actually rather take your questions, and maybe with your questions, we can dive into more stuff, and I can also get to some of your questions. So I can imagine that you might have some questions.
Yes, we have quite a few questions, James.
Okay.
And thank you for that awesome presentation. I know I certainly learned a lot. I have a few questions of my own, but I'm going to save those for later. Okay, so we have, I'm just going to start with the most recent questions and work backwards towards the beginning of the presentation. Some of the questions are about garden soil. Here's one. Is my garden mostly what I inherited by living in the valley, or have I and the previous owner changed it over the past 70 years?
Well, I mean, that excellent question, actually. Boy, what a smart group here. You inherited somebody else's soil, so however they were managing it, you probably, it's possible that it has changed. It might be changed for the worse if it was farmed intensively for 70 years without a lot of paying much attention to organic matter, because organic matter goes away over time. I mean, it doesn't always, but if you till it a lot and you're constantly extracting from it, you can end up with low organic matter soils. And what does low organic matter soils mean? It means less carbon and energy and less biological activity and less ability to actually accumulate more organic matter. So over time, 70 years of tillage and not accumulating organic matter, you are having less cation exchange capacity in that soil. I know farmers who have done the opposite, who have spent their lives trying to accumulate more organic matter in the soil to the point where they actually probably could reclassify the soil. And some of them are, and it's a bit of a diminishing returns at a certain point. I mean, if you have between 4 and 5% organic matter, and if you're serious at all about doing any sort of production, you really should get a soil test. And then otherwise you're just sort of guessing or just, hearsay. But if you have 4 or 5% organic matter, that's pretty good. And it doesn't sound like very much, but it actually has a large impact. And I'm not talking organic matter like sticks and leaves. I'm talking about the broken down leftover sort of organic matter that makes the soil dark in color. So yes, I think is the answer to that. You can inherit that.
That's great. And so a couple related questions. Well, what makes organic fertilizer better than good old Miracle-Gro? And what are we doing to the soil when we use Roundup?
Well, I can't really say what we're doing to the soil using Roundup without kind of venturing into opinion. There is peer-reviewed science on that, but I'm just not going to really wade into that right now. I mean, I farm organically mostly because I really love food, and it's a great way to teach soil science, because when you're managing organic matter to produce food, it's kind of like the ultimate sort of biological farming experiment. And I mean, the difference between organic fertilizers is that they are essentially just organic matter. I mean, When you're buying bone meal, that's organic matter. When you're buying fish meal, that's organic matter. When you're buying flaxseed meal, that's organic matter. And these special kinds of organic matter we call fertilizers. And in the industry, they call them specialty products. And they have different carbon, they have different amounts of N, P, and K and other micro and macronutrients like, crustacean meal or something like that. Might have a lot of calcium in it. And so the thing with these special kinds of organic matter is they're just like any other kind of organic matter. They need to be broken down by the billions in a single pinch first before the nutrients are released in a plant available form. So in order for those kinds of fertilizers to work, you have to feed the soil, and those fertilizers do feed the biota in the soil, which accelerates this process by which this nutrient, available forms of nutrients, leak out eventually. But that takes time. And the timing isn't always perfect on that, because you need a lot of nitrogen early in the spring, but the soils are still cold, and because of the laws of thermodynamics, the bugs are not moving as fast as we want them to, so you might have to add a little more juice on there. Now, something like a Miracle-Gro or some sort of chemical fertilizer is essentially the fertilizer already in its available form, and you just give it to the plant. And conceptually, there's really nothing wrong with that, except that it does sort of ignore the most important part of it, which is the health of the soil and the biota that live in the soil. And so by kind of sidestepping the biota, maybe over time people forget about the biota, or maybe never even knew about the biota. And so over time, those soils will become less biologically active because we're not feeding the carbon and the energy to them. Also, those types of fertilizers tend to accumulate salts, which changes the salinity of the soil, and the biota respond to that, so often negatively. So,
Great. Folks, keep adding your questions to the bottom. I'm going to keep going backwards in time just to grab all the early questions, and then I will come back and get your questions, and I think we will have enough time. James, here's a question about wildfire and soil, or fire and soil. How does frequently recurring wildfire affect soil health? And by that, fires that occur in the same area every year, or on a greater frequency.
Yeah, well, I really don't know. I'm not an expert in that at all. We do know, and I'm sure most of these listeners that are here tonight know about these, the importance of fire for ecosystems, and especially for certain germination of certain seeds, and for clearing out certain underbrush and non-natives and that sort of thing. But I can't really speak authoritatively on that. However, conceptually, in a very simplistic way, what you need to think about is when something is burning, the carbon and the energy are being released. And what's left behind? Ash. And what is ash? Mineral nutrients, right? So in the Willamette Valley, for the last century or so, when there was grass seed and burning of fields, and that's not just the last century. I mean, this is the Native Americans practice this as well as a way of changing the habitat. By burning the forest, they leave behind all these nutrients, and then the grasses, and that in conjunction with grazing animals, makes mollisols, which provide more nutrients for humans. So you might be thinking, well, can I just take the ash from my fireplace and put that in my garden? Well, you really wouldn't want to do that, even though conceptually it's a good idea, conceptually. But what you're not taking into account is that it drastically changed the pH of the soil. And that's the amount of acidity or alkalinity in the soil, which is a super important thing, which is another reason you want to get a soil test. But I would be happy, just for the heck of it, to look at somebody's soil if they wanted to, give us an address. That might just be fun just to do for 1 second here. How about where you live, man? Or somebody else? Yeah?
Somebody want to plug in their address? or approximate address?
No, we need an address.
Okay, here you go. We have one from
Some people
Melissa.
might be. We got something?
We have one from Melissa.
All right, I see that right there.
Oh, you got it? Okay.
I do. I can see that. It's the 2560D highway. Is that right? That's not a typo. So I'm going to take us to share screen, and we're going to go to the soil, Google Earth, the soil plugin. D highway, Hood River. Wow, Hood River. How's it going up there in Hood River? Now let's go and check it out. There we go. Oh man, I miss going to Hood River. Okay, now we're up like in probably orchard country. And let's see, there's D highway. And it just takes a look at all these orchards here. What's mostly there? Is it pears? Okay, we've got some sort of raging waterway here. And we can see that the contours of the soil, they roughly follow that waterway. So think about it. This waterway occasionally floods, and it has maybe at other times had enormous floods backing up into it. Because this flows into the Columbia. And the Columbia overflowed 14,000 years ago. The largest floods ever known to have been on the planet Earth happened here. And the water came up into this and carried lots of silts and spilled them up onto this soil, which might have otherwise not been such great soil. So let's just look in this orchard here. What we have here is something called, I never heard of this. There are 20,000 soils. I haven't heard of them all. This is called Weist. I don't know. And it's a Eric Fragioquept. It's an insectisol, which probably means that it doesn't have enough organic matter in the surface rhizomes to be a mollisol. That might be one thing. It's an aquept, meaning it's pretty wet. Aquept. Let's look at it up close. And we can see it has 2.5% organic matter in the surface. Look, it's got 15% clay and 14% sand, and the rest is silt. Now, we didn't have much time to talk about this, but there are different size particles in soil: sand, silt, and clay. Sand is a large piece of primary mineral that's from 2 millimeters down to 0.05 millimeters. Silt is anything from 0.05 millimeters down to 0.002 millimeters, and anything smaller than that is considered clay. And so the size of the particles kind of reflects the size of the pores. So if you have a lot of sand, you have a lot of sand-sized pores, and they drain rapidly and don't store a lot of water or nutrients. Clayey soils have a lot of small pores which hold water. They stay cold, wet longer, and they tend to have higher cation exchange capacity. And silt is sort of somewhere in between. Now, you may have heard of the term loam, and what loam is, you probably all think, oh, loam is good. Loam is good. You know why it's good? Because it's approximately equal parts sand, silt, and clay, which means it has approximately equal parts sand, silt, and clay-sized pores, which means it drains and it retains water and it holds nutrients. So I didn't actually go to here's the actual address right here. Let's see what's underneath of there. Now this is a zero fluvent. And what this basically means is this is probably just a big sandbar. You can see how this river curved around here. It probably used to go right through here, and it's probably flooded here on giant scales at one time. And this is probably a pretty sandy soil, I'm guessing. And let's just see if it gives any data. It probably doesn't. Oh, it does. Percent sand, no data. But look at only 7% clay, and I'm guessing it probably has a lot of sand. Look at the organic matter, less than 1%. Look at the cation exchange capacity. Very low because you don't have much clay or organic matter. Those are the two sources of cation exchange capacity. Not any salts. pHs are pretty high. And I'm guessing you're probably not gardening there. Is that correct? And if you are, you're probably somewhat disappointed.
Thanks.
Anyway.
A comment and a couple questions.
Sure.
Somebody really likes your shirt and wants to know the significance of it.
Excellent. Well, why don't we
And
just
and then somebody else says, please tell me that James has shirts for sale with soil-related quotes on them.
Oh my God. I don't know. This is not a plant, folks, because this is what I was hoping to get to, and I just thought I kind of forgot. Here it is. So I sell these shirts. That's right. Oh, hang on. Can you see that? Or hang on. I gotta do that. I'll share the screen. I sell these shirts, and 100% of the profits from this shirt goes to funding my student interns at the student farm. Now, these are the kids, folks. Go to soilforward.org right now. Just do it. Soilforward.org and buy one. I have them in ladies and in gender neutral styles. And they're all black with white. And that's just Arial bold font. Nothing special. But the 100% of the profits of these goes to funding the future. Right now, I have 8 interns that I pay through the sale of fruits and vegetables. We don't receive any funding from the university. And I've been running the student farm for 20 years as a volunteer myself. And I have had 10,000 students come through the student farm in the last 20 years. And I've had over 100 paid interns through the sale of fruit and vegetables. And you know how I did that? I grew food. And then I exchanged that for money because it has value, because it has carbon, energy, and nutrients in it. And it's called food. And I turned the land into food, which I turned it into money, which I could pay these students to learn how to grow the food. You see how it works? And my students are the most awesome. I have over 100 interns. I keep in touch with all of them. They have gone on to become agronomists specializing in organics. Many of them have their own farms. They work on farms. Some of them have gone on to have jobs in government and are changing the policy around soils. So I'm very excited to offer you this shirt. Now I'm going to tell you one thing. If you wear this shirt, you have to be prepared for people screaming at you from anywhere in the world saying, soil! Okay? Just saying, you got to be ready for that. Now, I also happen to have these shirts in both Klingon and in Vulcan. I happen to be wearing the Vulcan shirt today. And even on Klingon, they have soil because they eat something. And same with Vulcans. So, you know, you probably know someone who's more Vulcan than a Klingon. You probably are and the other way around. So please, won't you go to soilforward.org and purchase a shirt for the kids? For the kids. Okay.
Do it for the kids, people.
Do it for the kids. I mean, they gotta live here. The rest of we're all gonna be gone. And they gotta like deal with all of this. And I swear to God, my students are actually, they're ready. They're ready. We've been actually preparing for this moment for 20 years in my club. The inevitable perturbations were coming. We knew that. And we've been preparing. Here's the one thing we didn't imagine, though. We couldn't imagine that it would be, we couldn't work together. We thought anything we could do together. If we're willing to all work together and all of us a little bit, we could still have fun and do it. And we just didn't anticipate that it would be something, a perturbation like this. And I've told my students for decades now that you have been warned. The inevitable perturbations are coming. You have to be ready. In your lifetime, it's going to change. I just never thought it would be in my lifetime. But as it turns out, it is.
Okay. We have time for some more questions, and I got a few I definitely want to get to here.
Okay.
Here's a question. So bigger plants with deeper roots, for example, trees, increase the depth of topsoil? And is it because of the growth-death cycle?
Yes, I mean, trees, if you've ever dug up a tree, you'll notice that the roots are actually pretty big. And there are fibrous roots. And most trees have most of their roots near the surface. And that woody root material takes a long time to break down. So yes, they contribute to organic matter. If you walk around in the forest, you'll see you'll feel that almost hollow feeling of ancient dead wood. That's a lot of organic matter there. But actually grasses, which aren't quite as dramatic, actually contribute quite a bit more organic matter below ground. I mean, think about it, a grass plant, most of the plant is underground, and it's sort of sending up like an antenna, like an antenna pushing it up, and you can cut it and you can eat it down and it continues to come up. Where a tree, it grows from the tips out. And if you cut it down, it doesn't really grow back. I mean, some do, of course, using coppice. But so, yes, they contribute to organic matter in the soil. And what was the second part of that question?
Is it because of the death and growth cycle?
Yes, of course. And in fact, that's really what's going on, is living and dying and living and dying and living and dying. And that just keeps happening. I mean, think about it. I mean, where are all the dead elephants? I mean, if it wasn't for decomposition and decay, we'd be 6 miles deep in elephants on this planet, let alone everything else. So where is all the dead stuff is the question. I mean, where are all the dead birds? I mean, they die by the billions a day probably, and they just go under a tree and they biodegrade and they go back into the cycle. And so this tissue in this plant, you know, is going to go into the soil eventually, pretty soon. I've already killed it. I'm going to throw it out the window of my apartment. It's going to eventually end up in the soil. And it will be eaten by the bugs that will ooze out the enzymes and dissolve it. And then when they dissolve it, a little bit of that gets away and it goes to the next plant and gets taken up by the next plant, which then captures more energy from the sun, carbon from the atmosphere, makes a big plant, and then it dies and it goes back to the soil. And so there's this cycle of nutrients happening in the biomass. At the same time, though, rocks are dissolving and releasing those nutrients, which is the basis of it all. And in the end, we end up with stuff like this, garbanzo beans. I mean, that's food. And cornmeal. I mean, this is organic matter. And it biodegrades inside of us and releases, and it's a decomposition happening inside of our gut. Look, I don't know if you know this, but there's a hole here and there's a hole back here, okay? And there's a tube going through your body. And inside of that tube are the same bugs that are in the soil. And what are they doing? They're oozing out enzymes, dissolving the food that you ate, which then the nutrients go into your bloodstream and get pumped to every cell in your body. And that's how you live. And you breathe in oxygen and you exhale the carbon that's inside of here. And you get the ash minerals and you incorporate some of that carbon too, but you exhale 2/3 of it.
Great. Here's a question from someone who's interested in using clay in art like paint and stenciling.
Wow.
How many shades of clay do we have in the valley?
Yeah, I mean, in the valley, wow. I mean, how many shades of color are there? You know, it's of course it's an unanswerable question, but the Willamette Valley is most of the colors that are in pigments of paint are actually not so much from the clays, although there are some spectacular colored clays, but a lot of those clays are transitory in their color because as they get oxidized, they change color. But still, most of the colors that we see in natural pigments are from oxides. And you'll see more of those up off the valley floor, especially the reds and the yellows and the pinks and the really intense oranges and stuff like that. But in fact, our state soil, I don't know if you know that, but we have a state soil. It's called Jory. And Jory is this beautiful red, flaming red colored soil. And if you drive up out of the valley floor, up a little bit above 400-foot elevation or so, you'll start to see those road cuts with those really red soils. And also, if you go out on the coast and you go to the coast in Newport or wherever and take a left, and you'll be driving through canyons of Spotosols. And those canyons of Spotosols are these incredible oranges and yellows, and you could collect those for paint. Now you might have to grind those a little bit. So clay, maybe there's some very interesting colored clays, but I think that it's mostly oxides, if that answers the question. But how cool is that?
Thank you. Here's another gardening question. What are your thoughts on no-till gardening? For a small home garden, are there advantages to not tilling the soil or pulling up the plants by the roots after harvest, but just adding broken down compost on top and planting directly into that?
Yeah, I mean, that's kind of the holy grail is minimum disturbance. I mean, the more you disturb soils, the more oxygen you're introducing, which makes the biota eat organic matter more rapidly and exhale it as CO2. See, carbon in organic matter in the soil is transitory, and it sort of stays in the soil longer if there are pockets in the soil, very small pockets, that are low oxygen environments. And that's like inside of a little clump of soil can be very low oxygen environment, but in between the two clumps can be very high oxygen. And that's what you want. You want diversity in the habitats. Some of them really wet, some of them really dry, some of them cold, some of them warm, all different sizes, because the diversity of habitat begets the diversity of organisms. And the billions in a single pinch, instead of being a billion of one thing, there's tens of thousands of different species. And that's what you want. Diverse organisms lead to diverse functioning and redundancy of function. So when there is disturbance, they can deal with it. Where if you continue to disturb soils over and over and over, you slowly start to take out the diversity to the point where it starts to collapse and it can't process certain kinds of minerals or nutrients or carbon and energy. So minimizing disturbance is the goal. Eliminating disturbance is kind of pretty hard to do because agriculture, by definition, is about minimizing diversity. You don't have a forest, you have a cornfield. But does the cornfield have to be 7,000 acres with no weeds? Or maybe a few hundred acres with a little bit of an allowance for some cover crops and weeds to give it more diversity? So it really is about scale, in my opinion. And so for the home gardener, trying to eliminate disturbance is laudable. And if it works for you, really, it's really what you want to try and do. And by just adding more organic matter to the surface, and certainly don't pull your roots out of some of your tomatoes, just cut them off at the surface. Because what is a root? A root is carbon and energy. And actually, within 2 or 3 millimeters of every root hair, like even these tiny little root hairs that you can't even see here, those little root hairs, within 2 or 3 millimeters of that root is where the biologic diversity is greatest in soil. And the reason that is because roots leak out sugar water. And what is sugar? Carbon from the atmosphere and energy from the sun. It's food. And so these plants leak out 10% of their photosynthetic production. They're giving away to the bacteria and fungi that live in that little area, which is called the rhizosphere. And in the rhizosphere is where the biological activity is greatest. And the reason that the plants do that is because that's how if they can cultivate the bacteria and fungi that live near the roots, they get more carbon and energy, or they get more nutrients by feeding those bugs. So by leaving the roots in the soil after the plant is dead, you're leaving all that biota in place. Plus, look at this big root here. Eventually, that's going to be eaten and exhaled as CO2. And what do you have left? A big pore in the soil. And big pores drain into the force of gravity, and oxygen comes into the soil. So over time, roots living and dying, living and dying, living and dying, leave these castings of the roots and all that biota. And so that's so now you're like really starting to think about how soil works. And once you understand how it works, then you can sort of start to think about how and why you would want to minimize disturbance and grow your garden in that manner.
On a related note, I've heard soil has a hard time recovering from compaction. Is the solution just to add organic matter over time and let it heal itself?
I mean, I would say yes, over time. It's certainly, you know, after humans are extinct, I mean, the soil, look, the soil, everything is as it should be in the soil already. The soil's fine. It's us that's in danger. And yes, large machinery under wet conditions compact the soil, which make it very anaerobic, all small pores, all wet all the time, which blocks off the soil beneath from ever getting any air and makes the soil on top sort of sitting on top of a cold, wet bunch of soil. Sooner or later, and you can do this yourself by growing certain kinds of plants that will penetrate that, or you could break it up at least once and then get some plants to grow in there. Over time, yes, but it might take decades, you know, under extreme conditions, it might take many decades to eliminate that. But it can be done. And think about it. How is that plow pan getting, that compaction zone getting broken up? A root is growing into it. Think about the pressure of the energy that it takes to push a root down into the tiniest root hole, the little pore you never saw, a tiny little, and then it gets bigger over time because it's growing, because the carbon is being fed into it. It gets bigger and it pushes the soil apart, and then it dies and it goes away. And now it leaves a big channel for air and water to move. And a recolonization of more roots will eventually fill those roots. And you know what? The where the energy came from to do that came from? I mean, it's literally energy breaking up plow pans like a jackhammer force coming from the sun, which allows for those carbon to carbon bonds to kind of just be jammed in and for that root to get bigger and push that root down in. That's power, baby.
Well, James, we've just got about 1 minute left, and I would like to take this time just to, again, thank you for agreeing to talk with us today and opening up and blowing our minds about the realities of the solar system and soil and everything else, energy and carbon and water and heat. I really appreciate it.
It's a miracle. I mean, you want a miracle? We're living it. I mean, the fact that we can, look at, I have the ability to inhale using muscles and energy and carbon from energy from the sun to exhale. And then I have this thing in my mouth and I can form these sounds that we've all agreed mean things. And that's going into your ears right now. And I'm creating a psychedelic experience inside of your mind right now. And we can talk about reality. Amazing.
I don't know if I'm going to sleep tonight.
No point in it. Stay awake, man. There's much to do. There's so much to do.
Soil
I don't
Forward.
have time. I can't believe people watch TV. My God. For God's sake, people. Their reality is just, if you're watching TV, you're not working hard enough. You're not doing the job that needs to be done, which is saving the soil. All right? So the least you can do is buy one of these t-shirts and help the kids save the soil for themselves. All right? Thank you so much. Super fun. Time for a little reward. You are all awesome. Thank you so much. Super fun to look at these chat comments. And we still have people here. My God.
I'm working on
God bless you.
You can see it behind me.
Looking forward to meeting you someday, Matt.
You too. Thank you.
Live long and prosper. Live long and prosper. Good luck out there. Carry on. Buy a shirt.